this next chapter 5, which is focusing on the Euler totient function. And we've got our lecture again tomorrow. I might pause for a bit tomorrow and do some general stuff focused on problem solving and proof techniques. It's a useful kind of pause in the proceedings, but we're going to continue looking at some new material today in the Euler totient function. So this follows on very closely to what we were doing last time. So what were we doing last time? Groups based on the set Zn. The Zn was the set of congruence classes modulo n. So it's this system of all the remainders that you get when you divide something by this is an object we're going to be studying, and because we want to know how the congruence classes behave, how the system of remainders behaves. And we're thinking of a general system Zn, but of course a lot of it will depend on aspects of the number n, aspects of the modulus n that we're looking at. Now, so there's two groups. There's one using the operation of addition of congruence classes and one using the operation of multiplication. The addition ones are quite straightforward. If you looked at last time, there's a Cayley table, an addition table for the group Z4 plus. So you've got all four congruence classes 0, 1, 2, and 3. You can add them all together. The group inverses are there. The 3 is the inverse of 1, 2 is its own inverse, and so on. And there's not a huge amount of interesting structure there. The Cayley table is very periodic. Each row of the Cayley table is just the previous row clicked one space to the left. There's not a huge amount of mystery here. But the multiplicative groups are very different. So we looked at two examples last time, Z5 and Z8, the multiplicative, so the group of congruence classes under the operation of multiplication. Z5 didn't cause any problem. Yeah, you can have all the congruence, well, you have to exclude the congruence class of 0. You can't let 0 into a multiplicative group because the number 0 won't have a multiplicative inverse. It won't be, there won't be anything that you can multiply by 0 that will give you 1. Z5 is okay, but for Z8, we saw that we can't let in everything because of this question of when elements have inverses. And we proved this lemma, where was it? It was just on the previous page. We proved this theorem, which said that an element of one of these things, so by an element we mean a congruence class of an integer a modulo n, it only has an inverse when that integer a is coprime to n, coprime to the modulus. So those are the only elements you can let into the group, because the group you have to have inverses. So anything which isn't coprime to the modulus you have to exclude. So for instance, with Z8, we only have the congruence classes of 1, 3, 5, and 7. The other ones, 0, 2, 4, and 6, they've been kicked out because they don't have inverses with respect to multiplication. So there you go. And we could look at some more examples, or in your own time, you can investigate some more examples of the modulus. I think that's one of the tutorial exercises down to do. But there does seem to be interesting structure here in these groups, and they're not so easy to kind of wrap up as the additive groups. So in particular, it's not even clear how big these groups are. For any, like if you just shoot a modulus at me, 272, I don't even know immediately how big the multiplicative group is going to be modulo 272. I first have to go and work out how many elements are going to be in there. How many congruence classes modulo 272 are actually coprime to 272. Okay. Could be a lot, or there could be quite, the number could be quite reduced. So we introduced this idea of the Euler totient function. So that was the definition. That was the thing we ended with last time. So the Euler totient function phi is a function defined on the integers bigger than or equal to 1, or bigger than or equal to 2, I guess. And it is simply the number of numbers, the number of integers in the range 1 to n that are co-prime to n. So it's going to be the size of the multiplicative group based on Zn. So this is something that we would like to understand. So this is what we're turning to now in chapter 5. So we just begin by repeating the definition. Okay. So our first task, we're going to say a bit about Euler's totient function, but the first task is we want some way to evaluate it. We want some way to figure out its value, given an input n, given an argument n. Now, we can do that using the definition. So if I take that number 272, whatever, I can just patiently go through all of the congruence classes, 1, 2, 3, 4, 5, 6, 7, all the way up to 271, and check them all for being co-prime to 272. But it's quite a bit laborious. It's effectively just some kind of trial and error process. At the end of it, I will have identified all the congruence classes that are in the multiplicative group, and I can count them, and I then know the value phi of 272. Okay, that's all well and good, but then if you give me another problem, 276, I've got to go and repeat the whole process. And it's another trial and error process. And I'm not learning anything really about the structure or about the deep. I'm not getting any deep understanding of the Euler totient function. So what we would prefer is some better way of evaluating it, some better way of thinking of its values, thinking of the value phi of n. Now there is such a thing, and I thought about the ways to. It may be better to present this as a kind of discovery thing, and maybe not show you the formula straight up, but try and discover the formula, so to speak. But the approach we're going to take here is just look at what the formula is, and then think about how we're going to prove it, or how we might prove it. So we'll understand. Yeah, we'll get to know and understand the result first. So it's a nice formula there. Phi of n equals that. Now, what is that? Okay, there's a big pi there, so it's a multiplicative formula. It's a formula involving the capital pi. So it's a product of all these things. So it's the product as I runs from 1 to r of all this stuff here, which is depending on pi and ai. Now, pi and ai are very meaningful. They are the data from the canonical form of the integer n, right? So this formula is based on knowing, or it's based on using the prime factorization, the thing that comes from the fundamental theorem of arithmetic, the prime factorization of the integer n. So every integer n can be written uniquely as a product of different prime powers, and conventionally we numbered the prime powers p1, p2, etc. So that p1 is the smallest prime present, p2 is the next smallest, and so on. Although that's the fact that they're ordered in terms of size isn't relevant for this result. Okay. Just the fact that every integer does have one of these prime factorizations, and it's essentially unique. Okay. After the requirement that you order the primes in increasing order, it is exactly unique. There is only one such prime factorization that it has. These powers, or these exponents, ai, they're all integers greater than or equal to 1. They're just the power of that prime as it appears in the factorization there. So now you can understand how this formula for phi of n is put together. You simply, it's kind of like the product of all the prime powers, except it's modified a bit. You decrease each of the exponents by 1. You decrease each of the exponents by 1, so you're losing a factor of pi out of phi of n, and you're replacing it instead with just an extra factor, which is 1 less than pi. Okay. Has Andy shown you this formula in the cryptography? No. So just ignore that reference to chapter 3 of the cryptography notes. I think that was from a few years ago when there was a different lecturer, and she did make use of the formula before this point. So, I mean, let's just have a quick look at how we might apply that, just to make it concrete what I mean. So let's consider n equals 36. maybe we don't do this. So the prime factorization of 36, well, 36 is 6 times 6, so there's some 2's and 3's. Well, it's simply 2 squared by 3 squared, isn't it? 4 by 9. By 3 squared. 2 squared by 3 squared. So that's my P1 to the A1 and P2 to the A2. Okay. So 5n, 536 then, should be this product I equals 1 to R. So we got R equals 2 here. So it's just 2 primes appearing, of Pi to the AI minus 1 times Pi minus 1. So I've just got 2 indices, 2 values of I to go over. So the first one, I'm just looking at 2. 2 to the power of what? Well, 2 to the power of 2 minus 1. So it's just a 2. And that gets multiplied by a 1, 2 minus 1. Then you go to I equals 2. Pick up the prime 3, and 3 is raised to the power A2 minus 1. So that's 2 minus 1, so it's just 1 again, but this time it's multiplied by 2. So there seems to be 12. There seems to be 12 integers that are less than 36, which are co-prime to 36. It would be mad boring just to verify that uniquely. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is this a waste of time doing this? Verifying this exactly? Is it worth doing? Should I continue? Maybe it's worth doing once in your life. I've never done it as high as 36, but just to convince. So if we cross out everything that's not co-prime to 36, there should only be 12 things remaining. So anything which has a factor of 2 or 3 in it is not co-prime. So you have to cross out every second one to cross out all the things with factors of 2. It's easier to do them like this. Cross out all the things with factors of 2, and then you have to cross out all the things with factors of 3. So 3 is gone, 6 would be gone, 9 would be gone, 12 would be gone, 15 would be gone. Are these things going? Yeah, they're going 12, so I can just go down as well. Have to be gone. So is there 12 things left? Yeah, 3, 6, 9, 12. There's only 12 things remaining. These 12 things here. Yeah. Even better. 4 times 2. 12. So it works for 36. And whatever number you want to try, it'll work for it. You can even start to see some kind of structural thing, some pattern emerging. Look, all the numbers that were left there as being co-prime to 36, they've arranged themselves into columns nicely when written out in that kind of a way. And that actually feeds in. It's not exactly that same kind of an array, but there is a big array in the proof that we're going to look at the moment. And we do talk about identifying relevant columns in the array. So it actually was a useful thing to do. Because it's showing you there's something systematic going on. The fact that these numbers have lined up on top of each other, that's something systematic. And the length I went to rows of length 12. Well, that's kind of 12 is a product, some kind of product of 2's and 3's. So that's kind of significant as well. Okay, so there's some promising stuff here. But what we'd like to have is a proof. Okay, we can investigate it for however many examples of numbers n we want, and we'll always see this nice agreement and maybe some nice structure emerging in an array when we cross out everything that isn't co-prime to n. But we'd like a general argument that establishes that this formula is correct for any n. And that's what we're going to do. Now, it's a bit of a long proof, so I've split it up a bit into some smaller results. So we prove a couple of lemmas first and then do the actual proof. So we split the argument up. So we begin with just a sketch of how it is we're going to prove this. And then we'll identify the various bits we have to prove, and then we'll go and deal with those one by one. Now, the way we prove it is very much based on the type of formula it is. It's a formula which is multiplicative. It's built as a big product of things. And the things that are going into the product come from the prime powers that appear in the factorization of n. So we very much build it from the ground. We build the proof from the ground up based on that structure. Based on that structure. It's going to be a kind of an overall induction argument. But we're not going to induct on the value n. We're not going to start, say, proving it for n equals 2, and then proving it, and then showing that if it's true for n, it's true for n plus 1. We're not going to induct on the number n itself. What we're going to do an induction on is the number r. We're going to induct on the number of distinct primes there are in the prime factorization of n. So that's the induction. So what's the base case? The base case is when there's only one prime in the prime factorization of n. That's the special case of n being a prime power. Numbers like 9, 27, 256, power 2. So numbers which are just a power of a single prime. Those are kind of special. So we'll prove it first for numbers like that. So this is the result for a prime power. Phi of p raised to the power a is simply p to the power a minus 1 times p minus 1. So that's what this formula looks like if you've got r equals 1. If you've got r equals 1, you may as well not have that product operator there. So it's just one factor there. So you just get rid of the product operator, and you're just left behind with whatever the prime p is raised to the power a minus 1 times p minus 1. So that would be the base case of the induction. So we'll know that the formula is true for numbers n which are prime powers. But then we'll have to turn to, well, what about n? What about if n isn't a prime power? So that's the general case. Well, numbers that aren't prime powers, but they still have a very nice structure in terms of prime powers. Because we have the canonical form of an integer, that gives us a way of looking as an integer as a product of prime powers. So we'll have proved the base case of the formula, that the formula works for prime powers. And then we just have to show that it kind of multiplies together in the right way. Now this feature of the function phi is quite common in number theory and in mathematics. It's called being multiplicative. And what that property is that, so this is just this is the definition of this multiplicative property that you can attach to functions. A function is multiplicative if, well, it's completely multiplicative. It's called completely multiplicative if the function always behaves like this. If phi of a product is just the product of the phi values. So phi of a times b is phi of a times phi of b. If it was only that, that would be a function that's called completely multiplicative. But that's quite restrictive. There aren't many functions, there aren't many interesting functions around that behave exactly like that. So it's quite a restriction to place on something. A weaker condition is not that that holds for every a and b, but that it only holds for those a and b that are co-prime to one another. So if a and b are co-prime, then if this formula is always true, if the value of the function factorizes as phi of a times phi of b, then that function is called multiplicative. And we will prove that the function phi has this property. Phi is multiplicative. You see, two different prime powers are always going to be co-prime. If you have two prime powers and the primes are distinct, if the primes you're using for the two prime powers are different from one another, then they will be co-prime to one another. Yeah? So we can have A as being one prime power, B as being another prime power. And then the fact that the function phi is multiplicative will say, well, when you try to evaluate phi on the product of those two prime powers, you just evaluate phi in one prime power, you get something like this. You evaluate phi in the other prime power, you get something like this again, but with a different prime p, and you multiply the two together. But that's exactly the structure that the formula has. It just says take each individual prime power, take each individual p to the a part of this, and write down the new factor you have, p to the a minus 1 times p minus 1, and then just multiply them all together. So this, if we know the base case result, the result for prime powers, and if we know that the function phi is multiplicative, we put those two things together, And by an inductive process then, I mean, this would only deal with 2 prime powers. But by doing an induction type argument, we can deal with any number of prime powers. And we'll be able to construct this formula, establish that this formula is true. Is that okay? So we're going to do an induction proof on R, the number of distinct primes and the factorization of them. The base case for that induction is when R equals 1, but when n is a number like this, just a power of a prime. We'll prove that result directly, immediately after this discussion. Then we have to prove that phi is multiplicative. This is like the induction step, showing that if it's, you can always add in an extra prime factor into the formula, and an extra prime power into the formula, and it will keep the structure intact. Okay, so so that discussion there is just discussing the form that the induction proof is going to take. So we're going to induct on, where is it? So the base case is when n, the number n is just 1 distinct prime factor. And doing the induction, which is what we have to prove, we'll assume the theorem holds when the number n is k distinct prime factors, and then show it's true for every number with k plus 1 distinct prime factors. And then because you can write a number m which is k plus 1 distinct prime factors, because you can write it like this, and separate off the last prime power, then the other number that's left behind is just a product of k distinct primes. So that will be covered by the induction assumption. So the formula will work for that. But then we can apply the multiplicative property to say that phi of m is simply phi of this bracket times phi of this. Because we'll have proved the base case result, we'll be able to say that phi of this is this product. And because we'll have made the induction assumption, we'll be able to say that phi of this large product is the correct thing from the formula. Okay. So that will be the way we'll put it all together. So our first task then is to establish the base case. So now we're focusing on the case where we got n is equal to p to the a. Some prime p, some integer exponent a. So we have to go back to the definition of phi. Phi is the set of all the numbers that are co-prime to n. So what we're dealing with is a long list of numbers, 1, 2, 3, all the way up as far as p minus a. And the value of phi of p of a here is simply the number of numbers in this list, in this range, that are co-prime to n, co-prime to p to the a. We're going to do the same thing we did with the 36. We're just going to strike out, we're going to chuck out the ones that aren't co-prime. And then we can look at how many are left behind. And that will be the answer for phi of n, phi of p to the a. So how many of those numbers there are not co-prime to p to the a? Well, how can it happen that you are not co-prime to p to the a? If you're not co-prime to p to the a, it means you share a factor with p to the a. But what must that factor be? What kind of factors does p to the a have in order to share with another number? Oh, only p, effectively. Factors of p to the a are, well, p squared, p cubed, all the way up as far as p to the a itself. Okay. So because p to the a is a prime power, its only factor essentially is p. It's just repeated a certain number of times. So for any integer z, you can see there in the middle of this paragraph, for any integer z, z is not co-prime to p to the a if it has a factor of p in it. Or in other words, if z is some multiple of p. Now they're easy to strike out of the list because the first one on the list will be p. Working from the left, the first number which fails to be co-prime to p to the a is p. The next number on the list will be 2 times p. The next number will be 3 times p, and so on. It's just all the multiples of p. They all fail to be co-prime to p to the a. And secondly, they are all of the numbers that fail to be co-prime to p to the power a. So the multiples of p are p, 2p, 3p. How high do you have to go? When do you meet the last multiple of p? Well, the last multiple of p you meet is the last number at the end of this list, p to the a itself. That's the very last number you meet. And if you want to emphasize it's a multiple of p, you write it as p to the power a minus 1. How many numbers have I written down there? Well, I'm not sure. It's got dot, dot, dot in the middle, but when you look at it closely, you can see that they're counting themselves. I've got 1p, 2p, 3p, all the way up as far as p to the a minus 1 times 1. So the number of numbers on that list here is p to the a minus 1, isn't it? Because they're counting themselves. 1, 2, 3, 4, 5, up as far as p to the a minus 1. All those multiples of p. So we're striking out p to the a minus 1 numbers off that list in 5.9. So the number of things that are left is simply the number of things that were here to begin with, which is p to the power a minus p to the power a minus 1. 5p to the power a must be p to the power a minus p to the power a minus 1. Okay? Because this number p to the a is the number of numbers in the list to begin with, and we're chucking out this many, which are not co-prime, to n, to p to the a, and there's p to the a minus 1 again. So simply how many there were at the start minus how many are chucking out. And that factorizes into the required form. Simply take out the factor p to the a minus 1. We've got p to the a minus 1 times p minus 1. And that's the formula. That's exactly the formula we were trying to prove. Okay. So that's the special case of the Euler totient formula in the case where r equals 1, where your number n is just a prime power itself. Well, that's great. That's the base case of the induction proof dealt with. Okay. So we know the formula is true for prime powers. We now just have to establish that it's true for all numbers. Okay. So now we come to proving that. See, the second step we outlined in the sketch proof, we now have to prove that the function phi is multiplicative. Okay, so we have to show that it has this property, that if you take two co-prime numbers, a and b, phi of the product a times b is phi of a times phi of b. So we need to argue carefully about co-primeness. Now, co-primeness is defined in terms of greatest common divisor. Two numbers are co-prime if and only if their greatest common divisor is 1. That's the definition of co-prime. So now we're also dealing with congruency. So we'll just recall a result we had from before. I think I proved this either in the lecture or in the tutorials. And this was that the greatest common divisor matches well with congruence classes. By that we mean this result here, lemma 5.3. If you have two numbers, a and b, that are in the same congruence class, then they have the same greatest common divisor with n. So that's nice. That means you can speak of the greatest common divisor of a congruence class, because every integer in that congruence class has the same greatest common divisor with n. So it makes sense to say the greatest common divisor of that congruence class with n. The other result is one special property of co-primeness, greatest common divisor. This says, well, when is u co-prime to a product v times w? That's what the left-hand side of this equivalence is saying. The greatest common divisor of u with v times w is 1. Well, this result is saying, well, that's equivalent to u being co-prime to v and u being co-prime to w. Okay. So something is co-prime to a product if and only if it's co-prime to both of the factors. That's also easy to understand in terms of canonical forms. I mean, a number u has number u will have some kind of prime factorization. The product v times w will have some kind of prime factorization. Because of the uniqueness of prime factorizations, the prime factorization of v times w will be the product of the prime factorizations of v on the one hand and the prime factorization of w on the other hand. And what does being co-prime mean? U is co-prime to the product v times w if none of those p's, if none of those prime factors is the same as any of the prime factors we see here. So p, q, and r, pi, qi, ri are all prime. So these are prime factorizations we're looking at here. And u is co-prime to v times w if and only if none of the pi's equal any qi or ri. So if none of the primes you see in the prime factorization of u is the same as any of the primes you see in the prime factorization of v times w. But you can break that down as saying none of the p's are equal to any of the q's, as one statement, and none of the p's are equal to any of the r's. That's the second statement. But the first of those says p is q, or u is co-prime to v. The second of those says u is co-prime to w. Okay. So this gives us a way to, we can appreciate this lemma. I call it lemma 5.4. We can appreciate lemma 5.4 from this. Is that okay? Is any about that? So these are some small little preparatory lemmas we need for establishing that the function phi is multiplicative. So we should return to that now. So we give a proof of 5.4 here. It can be proved fairly directly. It's just using the definition of coprime, and I think we've already proved the various parts of it really. So one direction of this, I've said we've already done. It's one of the exercises we've already done with it. U is coprime to v, and u is coprime to w. That implies that u is coprime to the product v times w. That's an exercise back from 2.3. So that's already been established. The other direction, okay, we can do it now. Suppose u is coprime to the product v times w. Then by an earlier exercise, we've seen that that's the same as saying that there's a linear combination of u and v times w that is equal to 1. So there it is. There's some linear combination of u and v times w that's equal to 1. But that same linear combination can equally well be viewed as a linear combination of u and v, or as a linear combination of u and w equal to 1. So it fulfills many roles. So we are also looking at a linear combination of u and v equal to 1. So that means u and v are coprime. But simultaneously, we're looking at a linear combination of u and w equal to 1. So therefore, u and w are coprime. So using this result that being coprime is the same as having a linear combination equal to 1, that's true from exercises 2.1. That means that u is coprime to v times w. It is also coprime to u, v and w individually. Okay. So those are preparation lemmas for this biggie result. Now this is the, okay, you see the proof of this lemma goes, oh my God, it's 2 half pages, so it's more or less a page long. So this is the this is the guts of the argument. We said we're going to prove this formula for phi by an induction proof. This is really the induction step, proving that the function phi is multiplicative. And the proof keep trying to say, oh, I want to point out that thing there, and I go. The proof is based on this array. So this now looks kind of like it's not exactly like, but it's kind of doing the same thing when I laid out the numbers 1 to 36 there. We crossed them all out. It's a similar thing here. So what we're going to do is prove that the function phi is multiplicative. So we have to prove that phi of a times b is equal to phi of a times phi of b. So we're going to lay out all the numbers from 1 to the top number a times b. We're going to lay them out in this grid. And we're laying them out in an a by b grid. So we've got a rows and b columns. So in the top row, you've got the numbers 1 to b. In the second row, you've got b plus 1 up to 2b, and so on. Okay? So you're laying out all those numbers like that. And we're going to talk about this array of numbers. And we're going to cross out all the ones that aren't co-prime to the number a times b. And look at what's left, and look and see that that counts up in the right way in order for the function to be multiplicative. So this is the formula we're trying to prove now, that phi of a is phi of a times phi of b. And we're doing this under the assumption that a and b are co-prime. We're going to do it directly. We're going to count the number of numbers in this range, 1 to a times b, that are co-prime to ab. Doing it in a special way and show that it is also equal, or it agrees with the product phi of a times phi of b. So that's why we've laid them out in this array, which matches with a and b. So we've got a rows and b columns. Now, by this lemma 5.4 that we've just looked at, a number is co-prime to the product a times b if and only if it is both co-prime to a and co-prime to b. And that's because, yeah, if it's co-prime to a and co-prime to b. I don't think we're going to have time to finish this, but let's just say a little bit more about that array. The way we've laid it out, the array consists of b columns. When you look and when you focus on one column, say focus on the first column there, you've got 1, b plus 1. The next number will be 2b plus 1, running down the first column, then 3b plus 1. All of those numbers, they're all congruent to each other modulo b, because they're all a multiple of b plus 1. So all the numbers in the first column are congruent to 1 modulo b. So if we want to search for the elements of this array that are co-prime to b, one of our earlier lemmas, the lemma 5.3, said that if two things are in the same congruence class, modulo b, then they're either both co-prime to b or they're both not co-prime to b. Being co-prime to b is a property that's shared by the whole congruence class. So these columns are the congruence classes modulo b. So the numbers that are co-prime to b, they're going to fill out a whole column. Okay? So either all the numbers in one column are going to be co-prime to b, or all the numbers are going to be not co-prime to b in any particular column. Okay? So when we identify the things co-prime to b, they're going to be certain columns. There's going to be certain columns that are co-prime to b. How many of those columns are there going to be? how many congruence classes are coprime to B? Well, that's exactly the value phi of B. This is where we start to see the result emerging. When we look at this array, we ask ourselves, how many of these things are coprime to B? Well, we don't know. But the answer is they will arrange themselves into columns. So either everything in a column will be coprime to B, or none of them will be. So they'll arrange themselves into columns. And how many will we see? How many columns will be coprime to B? Well, that's just the question of how many of these top representatives, how many of the entries in the top row are coprime to B? Well, that's simply phi of B. So that's a very nice thing that emerges about this array. And then we just do the same thing looking at A, okay? Looking along the rows, looking through that table by looking along the rows. Okay, but the argument is kind of delicate, and we just have to proceed quietly. We want to go through it at the right pace and not rush. So we'll finish that off tomorrow when I see you on Friday. But you can have a read through it yourselves. It's just a nice counting argument based on this array there. And then we might do a bit of catch-up work on proof techniques and stuff tomorrow as well. Some useful stuff.